In this video, I want to explain the differences between confidence intervals, which come from classical statistics, and credible intervals, which come from Bayesian statistics. And the example that I'm going to use to explain the differences between these two concepts is imagining that we are a doctor, and what we're trying to do is our patient has come to us and they have presented with a particular symptom. And the symptom which they tell us about, we're going to assume was the first symptom to appear. And there are four possible symptoms that we're imagining here. So we've got individuals that present with fever, first of all, headache, joint pain, and nausea. And as a doctor, what we're trying to do is we're trying to guess or estimate which disease or condition an individual has. And we've got four possible conditions here: colds, flu, food poisoning, and malaria. So we're going to sort of call these four, it might be a bit of a strong word for a cold, but we're going to call these four our possible diseases. And the numbers which are shown here in each column are the historical breakdowns of first symptoms to appear for each of the four possible conditions. So for a cold, we see that 10% of the time, the first symptom to appear are fevers. And 68% of the time, if you have a cold, then the first symptom to appear is a headache, etc. And I should say that these numbers are entirely fictitious. I've just made them up for this particular example. So because these are historical breakdowns for each possible condition, the sums in each of the columns here actually add up to 100%. So what this means is that for each of the conditions that we consider here, the first symptom to appear in our patients is always one of these four possible symptoms that we've noted down. And what we're going to do now is we're going to construct confidence and credible intervals that have a coverage which is greater than or equal to 80%. And crucially, we're going to try and construct intervals which are as close to 80% as possible, but not below that threshold. Obviously, trivially, we could obtain 100% coverage here if we said no matter what symptom an individual presents with, first of all, we say that they could have any of these four possible conditions. But being a doctor, we want to try and narrow down those options to allow us to treat the disease as best as possible. So something to bear in mind in all of this is how do we relate this back to statistics that we've been discussing? Well, the idea is that the thing that we're uncertain about here is the disease which a patient has. So this disease basically plays the role of a parameter. And when we construct intervals of uncertainty, essentially we are going to be constructing intervals which are composed of subsets of these four possible conditions. So our parameter here is a discrete parameter. And the thing which we have to hand is our data. And our data is the first symptom which our patient presented with. And what we're trying to do in statistical inference is we're trying to update our state of knowledge about the world in light of the fact that we've received our data. First of all, I want to start by discussing classical confidence intervals. And the idea with classical statistics is that you hold the parameter constant and you vary the data. And under that condition, what we're trying to do is we're trying to achieve intervals of uncertainty which at least add up to 80% and are as close to that number as possible. So what we do is we consider each of the columns and we consider column sums. And essentially what we do now is we're just going to circle those entities which when we add them together, we get at least 80%. So in the case of a cold, I've circled headache and joint pain here, and we see that if we add these two quantities together, we get 86%. So that is greater than or equal to our threshold here. Next, considering the flu case, here we only need to circle one of these numbers which corresponds to fever, because then we obtain 80% exactly. After that, we consider food poisoning, and we can obtain 80% exactly if we circle the numbers which correspond to joint pain and nausea. And so now we get 80%. And then finally, we consider malaria. And here we need to circle just the 50% and the 38% corresponding to joint pain and fever. And we see that these two numbers, if we add them together, add up to 88%. Okay, so that seems a little abstract. So how do we actually form our confidence intervals? Well, the idea is all we do is we take each row, so each possible first symptom, and we then just look up the circled objects and the diseases which correspond to those circled objects, and those collection of diseases correspond to our confidence intervals. So here, if an individual presents with fever, first of all, then we say, using our confidence intervals, that that individual could have flu or malaria. If an individual presents with a headache, first of all, then we say that that individual has a cold. If an individual has joint pain, then we say that that person could have a cold. They could have food poisoning, which I'm just going to write FP, and they could have malaria. So just to be clear, these are sets of objects here. And then if an individual presents with nausea, first of all, then we would say that that individual had food poisoning. So these are our minimum coverage confidence intervals. So what do they actually mean? Well, the idea is, what we say here is, no matter what condition an individual has, if we use these confidence intervals to associate symptoms with a particular condition, then we're assured that for whatever condition an individual has, so for whichever disease they have, we get the right answer 80% or more of the time. So here we're conditioning on a particular disease. We're assuming an individual has a particular disease, and if we use these rules that we've created here to link symptoms with diseases, we get the correct answer at least 80% of the time, and as close to 80% as possible. Next, what we're going to do is we are going to consider how we form credible intervals in this case. So to bear in mind in all of this is that our disease plays the role of our parameter, and our first symptom plays the role of our data. And remember that credible intervals, being a Bayesian concept, imagine that the thing which we're uncertain about is our parameter, so we vary our parameter and we condition on our particular data. So now the objects or the natural direction which to consider things is horizontal, opposed to the vertical case which we did in confidence intervals, which was a classical concept. So now we essentially consider row sums. But when we condition on a particular first symptom, we see that the row sum doesn't add up to 100%. In other words, we don't really have a valid probability distribution. So what we actually have to do is we have to normalize our table. And the way we do that is by forming the row totals. So if we go through here, we get 138%. We, by chance, get 100% for the second row. We get 98% for the third row. And we get just 64% for the final row. And so what we're going to do now is we are going to normalize each of the numbers in here by dividing it through by the row total. So now I've gone through and I've done this normalization here, and you can confirm for yourself that each row here should add up to 100%. There might be some rounding errors here, which mean it doesn't quite add up to 100%, but it's actually, in terms of decimal numbers, it's exactly right. So in forming credible intervals, what we're going to do is we're going to condition on our particular data that we receive. So now we're going to imagine that an individual presents with fever as their first symptom. And now what we want to do is we want to construct intervals of uncertainty, so select diseases here, such that we obtain at least 80% coverage. So here we see that for a fever, we imagine an individual could have flu or they could have malaria. That's the only way that we can obtain at least 80% coverage, and here we obtain 86% coverage in this case. Next, considering individuals that present with headaches as their first symptom, then we imagine that those individuals could have colds or they could have malaria. And so here we obtain an exactly 80% coverage. For individuals that present with joint pain, first of all, we imagine that they could have flu, food poisoning, or malaria. It turns out with rounding, actually what we get is a coverage of 82%. So bear in mind that 82% doesn't add up to these three numbers here exactly because I'm sort of neglecting a decimal point in each of these. Then finally, for those individuals that present with nausea as their first symptom, then we see that the only way we can obtain at least 80% coverage is if we imagine that those individuals have food poisoning. And so we get a 94% coverage in this case. Okay, so you can probably tell how we're going to form the credible intervals now, and I think it's a bit easier to sort of understand than the confidence interval case. Perhaps I'm a bit biased, but the idea is essentially what we do is we consider each of the symptoms and then we construct intervals composed of the diseases that we've circled in each of the cases. So in the first case, our credible interval composes those individuals that have flu and malaria. So the idea is that we would say that if an individual comes to us with fever, that they could have flu or malaria. If an individual comes to us with a headache, then we say that that individual could have a cold or they could have malaria. So quite extreme differences in outcome there. If an individual comes to us with joint pain, then we say that that individual could have flu, food poisoning, or malaria. And finally, if an individual comes to us with nausea, then we say that that individual has got food poisoning. So how do we interpret those credible intervals? Well, the idea is that in Bayesian statistics, we're conditioning on our data, and we're saying, conditioned on that data that we obtain, let's ensure that our intervals contain the true answer at least 80% of the time. So what that means is that no matter which symptom an individual presents with, if we use our rules to link symptoms with diseases, which is what our credible intervals are here, then we're assured to get the correct answer at least 80% of the time. So for individuals that present with fever, first of all, we're assured, if we say that that individual has flu or malaria, that we get at least 80% of the cases correct. Similarly, if we consider individuals that have headaches, if we say that individuals that present with headaches, first of all, either have colds or malaria, we get the correct answer at least 80% of the time for those particular first symptoms. So you see that what we're doing now is we're conditioning on our first symptom, whereas for confidence intervals, we were conditioning on the diseases. And there isn't a right and a wrong way to actually do this kind of conditioning. It just comes down to your perspective and which is more appropriate to the circumstance. Now what I want to do is I want to compare the confidence intervals with the credible intervals that we obtained. And so what I've gone and done now is I've underlined those entities which form our confidence intervals in the sort of purple colour here, and I've also underlined those entities which form our credible intervals, or are used to form our credible intervals, and those are shown in orange here. So what we can actually see here is that there is considerable overlap between these two intervals. And so what we see here is that for individuals who present with fever, first of all, in both the confidence interval and the credible interval case here, we say that that individual could have flu or could have malaria. And we see that because both of these objects, these numbers now, are underlined with both colours. For the case where individuals present with headaches, first of all, we see that the confidence interval actually just says that individual has a cold, whereas the credible interval says that they could have a cold or they could have malaria. For individuals who present with joint pain, then we see that both credible and confidence intervals say that those individuals could have food poisoning or malaria, but they differ in terms of what the other condition is. In the case of confidence intervals, we would say that that individual could have a cold, whereas in the credible interval case, we say that that individual could also have flu. Finally, for the nausea case, we see that both intervals just say that that individual has food poisoning. So the reason that I've compared these is because this illustrates quite a common outcome of doing an analysis with both of the different techniques, assuming that the sort of assumptions of the model are pretty much the same, which is that the confidence and the credible intervals typically overlap considerably. If you get very different confidence intervals and credible intervals, that's typically a sign that there's something different about the model in each of the cases. So for example, we might be using a prior which is quite informative in the Bayesian case. What else do we see? So what we can actually go ahead and do now as well to compare these two different types of interval are we can construct what is the credible interval coverage for each of the confidence intervals and vice versa. So starting off by considering those individuals who present with fever, first of all, well, we see that the credible intervals and the confidence intervals exactly overlap now, and we've worked out from before that the credible interval here is 86%. Remember that we obtain that by normalizing the rows by their sort of total and then summing together the object. So the 86% here quite clearly doesn't equal 80% plus 38%, but it does so when we consider our normalized table. So this is the credible coverage that we would obtain by using our confidence interval here, and that's the same as the credible interval that we constructed as well. Next, considering those individuals who have headaches. Well, here we see that the only object which is underlined with a purple marker, because we're considering confidence intervals, is the cold case. So actually what we have here is a credible coverage of 68% if we go and we use the classical confidence intervals. For joint pain, we see that we obtain the 18% here for the case of flu, with the 20% of food poisoning and the 50% for malaria. And again, using our normalized table, we get a credible coverage of 90%. And it's just worth pointing out that the 68% here is the same in both the normalized and the unnormalized case, because the row sum here actually equals 100% by chance. And then finally, in the last case here, when we consider individuals who first present with nausea, the credible intervals and the classical confidence intervals entirely overlap, so we obtain exactly what we had before, which was 94%. Next, if we consider the classical coverage, which results from using our credible intervals, what we need to do is we need to consider the column sums. So firstly, starting off with individuals who have colds, then we see that the only object which is lined with a orange marker is the case which corresponds to headaches, which is 68%. So our classical coverage is 68% in this case. For individuals who present with flu, we see that there are two entities which are underlined, the 80% and the 10%, corresponding to fever and joint pain, and so we get a overall classical coverage of 90%. Next, considering the food poisoning case, we see that the classical confidence intervals and the Bayesian credible intervals entirely overlap here, so we get the same coverage as we did before, which was 80%. And then finally, for the case of malaria, we see that there are now three objects underlined, which is different to what we had before, so actually what we obtain now is a coverage of 100%. So what does this exercise tell us? Well, the idea is that if we condition on each of the potential symptoms here, and we consider the credible or the Bayesian sort of coverage here, the credible coverage that we get, then we see that some of the time we do kind of as we did before. So for the case of fevers, we do exactly the same. For headaches, we actually don't predict as well as we did before. We only predict the sort of right answer 68% of the time. And for the case of joint pain and nausea, then actually, in both of those cases, we overextend our kind of limits. And so what we find here is that actually we are being a little bit too uncertain about the condition which we're trying to predict. Similarly, if we consider our classical coverages, so now what we're doing is we're conditioning on each potential disease, we see that in the case of colds, we actually only get the correct answer if we use credible intervals only 68% of the time. For flu, we sort of slightly go over the top and we're a bit too uncertain if we use credible intervals, whereas classical intervals would say that an individual just has fever. A credible interval would say that individual could have fever or joint pain. So here we actually go above our sort of 80% mark. And for the food poisoning case, we get exactly the same as we did before. And similarly for malaria, we go way above, and so we're sort of too uncertain here. Which of these intervals is preferable depends on your perspective. If it's right that given a particular symptom, we predict as many of the cases correctly as possible, then we want to use credible intervals. If, however, What's important is that conditioned on a particular disease, we get X%, or at least in this case, 80% of the sort of patients who come to us who have that disease, we get their diagnosis correct, then we want to use confidence intervals. And it also comes down to what is the sort of cost if we get things wrong, and what are the prevalences of these different diseases. Here I've assumed that the prevalences of all these diseases are exactly the same, and you can imagine how the optimal diagnosis might change if that weren't the case. In summary, there isn't a correct answer for which interval you should use. It depends on perspective. Although, reassuringly, in many of the cases which you'll consider, there is considerable overlap between the two different types of intervals that we come across.